I have some bad news. The bad news is I have one more electric vocab word to give you, and that is electric power. I'm sorry. I apologize. There's one more, just one more. Electric power, but we can make it a little bit easier by just calling it power. In general, and this is true for whether we're talking about mechanics, kinematics, electricity, whatever, power is the rate at which we use energy, right? So power is just E divided by T. Okay? In other words, energy divided by time. The amount of energy that a circuit uses divided by the amount of time that it uses. Or the energy that just one given resistor uses divided by the amount of time. Okay? So power is measured in the unit of watts. Something you've all heard of before, but maybe weren't quite sure what it was all about. So a watt is, unsurprisingly, a joule per second. So if we're talking about a 100-watt light bulb, right, what we're really talking about is that that light bulb uses 100 joules of energy every second. And that kind of feels like a lot. That's kind of why, intuitively, your parents or a sibling or somebody, whoever you may live with, whoever pays the bills, is scared about paying 100 joules for every second, paying for 100 joules of energy every single second, right? And so before this video is over, we're going to actually talk about how much that really costs. All right. So now this is the general equation. Power is energy divided by time. But here's the thing. In the electric world, we have a specific equation for power, and that is just I times V. All right. In other words, power is equal to the current moving through a circuit times the potential difference in that circuit, or you can look at it as just an individual resistor. The power that's used or dissipated by that resistor is equal to the current through the resistor times the potential difference across that resistor, all right, times the voltage across that resistor. Now, if we combine this equation with V equals IR, we see that there's a couple other ways that we could represent power. All right. First of all, let's just substitute IR in for V. All right. So then we would get P equals I times IR, which is equal to I squared R. All right. So let's say there's a problem where you're only given current and resistance. You can find the power in that resistor, or being used by that resistor, using this equation instead. Right. All right. We also know that I equals V over R, right? So let's do that substitution. Let's say put in V over R in for I. We have V over R squared times R. That gives us V squared over R. That is a third equation. So there's three ways that you can approach solving for power in problems that involve electricity in circuits. Okay, so you can use the IV method right here. You can use the I squared R method, or if you're given just the voltage and the resistance of the resistor, you can use this. Put them all down, put them all in your notes because they may all come in handy. All right? All right. So if we want to just apply this to an actual problem, let's take a look at this treatment of heart failure problem. Okay? It says that a heart defibrillator is used to enable the heart to start beating if it is stopped. Many of you guys have seen these before. Maybe some of you have actually used them, right? The defibrillator where it's like, clear, right? And then the person's heart stops and they're alive and, the Hollywood music starts and everything. Okay, so this is done by passing a large current of 12 amps through the body at 25 volts for a very short time, usually about 3 milliseconds. And so the first question is, what power, in other words, how much energy per time does the defibrillator deliver to the body? So that's part A. So I'm going to say part A over here. What is that power? Well, what are we given? We are given a voltage and we are given a current, right? It's a 25 volt signal and a 12 amp current in that electrical signal. So I would just use P equals IV, right? We have current, we have voltage. Makes this problem almost too easy, right? So we have the current is 12 amps, and we have the voltage of 25 volts, And so if I multiply those guys together, what do I get? I get the simple answer of 300 watts. In other words, 300 joules per second is being delivered to the body in that little, right? All right, this next question is, okay, that's how much power, but how much energy is really transferred? Whenever you have a power problem that's asking about energy, it's begging you to use this equation, right? Because this equation has energy in it. So in other words, if power equals energy over time, then we know that the energy being delivered is just equal to power times the time that the signal is being delivered, right? And in this case, the power, we just calculated it, it's 300 watts, all right? And it's being delivered for 3 milliseconds. So in other words, 0.003 seconds. If I put that in my calculator and I multiply those two, one of those questions you should be able to do in your head, it ends up being 0.9 joules, or let's say roughly 1 joule of energy is delivered. So it's kind of wild, right? It's like, the power is kind of high. It's 300 watts, right? But because it's sent over such a small time period, just a sudden burst of 0.03 milliseconds, or 0.03 seconds, then that means that you really only get a joule of energy, which is why that can happen without seriously frying your body. Pretty cool. All right. Lastly, I want to look at this problem of how much it costs if we leave the light on at night. Okay? So let's do that. Let's take a look at that question. So in San Diego, we pay 25 cents per kilowatt hour of energy. All right? Kilowatt hour is the unit of energy that power companies use to measure the amount of power used, right? It's better than a joule second because a joule second is, it's better than a watt second because a watt second is just a joule, and that's insignificant. That's not a lot of energy. But a kilowatt hour is a significant amount of energy that a house might use over a certain amount of time. Okay, so my question is, if we have a 100-watt light bulb that we leave on at night, let's say 8 hours, while we're sleeping for 8 hours, should your mom or dad, or whoever it is that pays the bills, should they really be mad? In other words, how much is that going to cost? Okay, how would we solve this question? I honestly would challenge you to pause the video and see if you can figure this out yourself. I think you can. It's basically just a conversion problem. But if you want me to lead you through it, let's go for it right now. Let us start by saying we have 0.25 25 cents, so $0.25, right, per kilowatt hour. All right, that's what we're starting with. And I am going to go ahead and say that I don't like this kilowatt hour. I want to go to my SI units. My SI unit would be watt seconds. So let's go there first. Let's convert there first. So I'm going to multiply this by, I'm going to say that in 1 kilowatt, there's 1,000 watts, right? And I'm going to say that in 1 hour, there is 3,600 seconds. And if I multiply those together, I get 6.9 times 10 to the negative 8 dollars per watt second. All right, I like watt second. A watt second is just a joule. So basically this is saying I pay 6.9 times 10 to the minus $8 for every joule of energy that our house uses. Okay, you see what I did there? Okay, so now this is what I want, right? And so if this is what I want over here, I want to get rid of watts and I want to get rid of seconds altogether. Okay, so if I have 6.9 times 10 to the minus $8 per watt seconds, I know that I am using a 100-watt light bulb, right? So let me multiply that by 100 watts, right? And I know that I'm doing this for 8 hours, right? So 8 hours is 8 times 3,600 seconds, right? So I take this and I multiply by 8 and by 3,600 seconds because there's 3,600 seconds in every hour. So if this is the price that I pay per watt second, I want to find out how many watts, multiply by that, and I want to find out how many seconds and multiply by that. And what do I get? What do I get? I get a value of $0.2 for one night. Okay, $0.2. That's it. That's 20 cents. So you can use this information as you'd like. I would probably get sassy about it, especially now that I know this, and I would say, you know, you're mad for this one light? Here's 20 cents. Pfft, 2 dimes. Mom, dad, whoever it is. And if they try to, you know, say, hey, no, you just cost me $5, you just cost me $10, then I would walk them through this problem. Not with me, I don't want to get in trouble, but you alone, because you can do it now, walk them through this problem and tell them it's just 20 cents. You'll try to do better next time, but as far as last night goes, not a big deal. All right, I'll see you in the next video where we do the grand finale dealing with the power of an electric eel.